Okay, yesterday we discussed bit more about the traffic signals. Okay, so we discussed the types of traffic signals. There are three types. We can use them in a coordinated way as well, and we discussed the benefits. Okay, then we discussed some of the terminologies, indications which are shown in the traffic signal. So you have the green interval, red interval, yellow interval, all or clearance interval. We discuss about the loss time, saturation flow rate, saturation headway, and all these things. Okay. Then in the end we did or one example where we found the capacity of a lane, and we found it using two methods. In the first method we were using the green time, the effective green time of the whole hour, and the second method we were using the saturation flow rate, okay, and the percentage of cycle which is effective green. So this is what we did last time. Moving on, in the previous example we just calculated the capacity of one lane. Okay, let us move forward and see how we can calculate the capacity of the entire intersection. Okay, so for that we will try to draw an equation. Okay, so every time the signal becomes green, every time we have a phase in the signal, we have loss time. Okay, and I explained last time that we have a startup loss time and we have clearance loss time. If you add them together, you will get total loss time, which is represented as TL here. Okay, so TL is the loss time in one phase. Okay, now one phase is for one movement.
Phase meaning what?
Huh?
Phase meaning?
Phase meaning phase.
Like period of time?
Huh?
Period of time?
Phase meaning the time you give for one movement. The time the signal has red and yellow and green, right? Okay. So from all that time you receive a portion for your movement, right?
Right.
When you are standing on a signal, it's not green for you every time, right? So you receive a portion of the total time as for your movement.
So the portion of the
That portion is called as a phase.
green light.
Green plus yellow and plus something else. Okay? Clear? So whenever the signal has a phase, it has a loss time as well. Okay? So, and the signal cannot have one phase, right? You have to give time for every movement, right? The signal does not have one movement. It has multiple movements, right? Right or wrong? I thought the sleeping time ends at 10 o'clock. Huh?
Wrong, right?
Yeah, it seems wrong. They are still sleeping. Okay, signal has more than one movement, right? Okay, so we need more than one phase. Okay, so let's say the number of phases are n. Every time we have a phase, we have loss time of TL. So if we have n phases, then the total loss time is n into TL. Okay, so in one phase there is a loss time of, let's say, 2 seconds. In two phases it will be 4 seconds. In three phases it will be 6 seconds. Okay, so TL is the loss time in one phase, and n into TL will give you the loss time of the whole cycle. Clear? Okay, this is loss time in one cycle. Then how much is the loss time in the whole hour? I multiply the loss time with the number of cycles I have in 1 hour. How many cycles I can have in 1 hour? Total time divided by time of one cycle. It will give me number of cycles. Okay. Number of cycles multiplied by loss time of one cycle. It will give you total loss time of the hour. Okay. From the total time, if you subtract the loss time, the remaining is called effective green. Okay. So total time of the hour minus loss time of the hour gives you effective green time of the hour. Okay. In effective green time, the interval between the vehicles is called saturation headway. Okay, the interval between the vehicles is called saturation headway. Okay, so if I want to find out how many vehicles I can have in effective green time divided by the saturation headway, the interval. Okay, this gives me total number of vehicles I can have in 1 hour. Okay, clear? This is the time I have in 1 hour divided by the interval between the vehicles, number of vehicles you have in 1 hour. Clear? Okay, this is the maximum volume you can have on an intersection in 1 hour with a signal. Clear? Any problem? Okay, now in this equation, what is H? Headway. Okay, and to be more precise, we call it saturation headway. Okay, but you can measure it in the field. It was discussed in the last lecture. TG, what is TG? Effective green time for 1 hour. Okay, this came from where? This thing, right? Okay, now here what is LH? Total lost time of 1 hour. From where did we get this? Okay, now here what is C?
Number of cycles.
No, time of one cycle. And what was L? Lost time in one cycle. Okay, and this L came from where? What is N? Number of phases. What is TL? Lost time in one phase. Clear? Okay. So TG has an equation. Then in the equation of TG, LH has an equation. An equation of LH, L has an equation, right? So I can put all these values back into the equation. Okay. So this is the simplified version. Okay. And after you put all the values which I have just mentioned, the final equation is this one. Okay, this was the actual equation, TG upon H. Cute little sweet equation. Okay, then we put the value of TG, then LH, then L, and okay, we make it a scary monster, which is this one. Okay, clear? So this is U at the time of admission. VC equals to TG upon H. This U when you graduate. Don't believe me, look at your pictures, the high school pictures. You will know what I mean. Now you understand. Huh? Okay. Okay, now look at the equation. This is for maximum volume for an intersection. Okay, look at the equation and tell me N is number of phases, right? N is number of phases. So what will happen to VC if I increase the number of phases? If I increase N, what will happen to VC? Decrease, right? Because N is subtracting, right? Okay, so VC will decrease. So increasing the number of phases will decrease the maximum volume. Okay, why? Because each phase has lost time. When you increase the number of phases, you are increasing lost time. Okay, you increase lost time, you will have less volume, right? Okay, now look at the equation. Capital C is cycle length. What happens if I increase C to VC? If I increase C, because C is in the denominator of the negative, right? So it will increase VC. Okay, so increasing cycle length will increase the volume. Why? Cycle length is what? Timing of the signal, right? So if you provide more time, you can have more volume. Clear? Clear? Okay, and this is what they are showing in the graph over here. Okay, so number of phases increasing, lost time is increasing, volume is decreasing. Okay, cycle length increasing, volume is increasing. Clear? Clear? Okay. So, for example, we have two phases. The maximum capacity is what? For two phases, right? Okay. Now, two phases means what? Two movements. Each phase is for each movement, right? One phase is for every movement. So two phases means two movements. Okay. Does an intersection have two movements only? No, it has more movements, right? So then two phases may not be practical every time. Although it gives maximum capacity, but I cannot provide it. Okay, because I have other movements as well. Clear? Okay. What about the cycle length? I cannot make two phases. Okay, I have to increase the number of phases because of the movements. But can I keep on increasing the cycle length as much as I want? Why not?
Because we cannot let one lane go for 6 minutes.
Yes. Okay. So cycle length means what? What is a cycle? From red to red. Okay. So it means what? You get one chance to move in every cycle, right? Okay. So if you missed your chance now, if you have red now, the next green will come in the next cycle, right? The next chance will come in the next cycle. Okay. If the cycle length is
Cycle is between green until the next green.
yeah, something like that. From red to red, you will get one green, right? In every cycle, you will get one green. Okay. So if you are in this cycle, your next green will come in the next cycle. Okay. So if your cycle length is 2 minutes, you will get a chance to move after every 2 minutes. If your cycle length is 3 minutes, you will get a chance to move after every 3 minutes. If your cycle length is 10 minutes, you all know. Very good. A guy with a cool head. Huh? Others are thinking what will happen to us. Huh? We'll fill our plans. Okay? So you get the point. Okay? So these are some considerations you have to keep in mind while you are designing the signal. You don't always look at the number. Okay? The number, okay. Now I'm looking at the highest number here. But is this possible? Okay? You have to look at, can I get two phases? Huh? Or can I have a cycle length which is up to 10 minutes or 15 minutes? Okay? You have to look at these things. Okay. Now, VC is maximum volume. Okay? How do we define capacity? Tell me. Maximum flow. Everybody agrees? Obviously. Not like this. Huh? Maximum volume flow rate. How do you remember this? Okay. So there are some people like this, right? They give you answer, everybody copies, and then they cross out their first answer and put the next one which is the correct one, right? Is that good? Maximum flow rate, yes, maximum flow rate. And how do you convert volume to flow rate? Yeah, peak hour factor. Okay, you divide by peak hour factor. So if I want to convert maximum volume to maximum flow rate, I have to divide by peak hour factor. Okay. Secondly, if I am designing the signal, I am designing anything. Okay, do I want the demand to be exactly equal to capacity? Huh? I want which one more, demand or capacity? Capacity should be more, right? Okay, so I should have a factor of safety. Okay, that factor of safety is V by C ratio. Okay, the factor of safety which we put in the design equation is called V by C ratio. V is demand and C is capacity. Okay, now you want which one to be higher? Capacity. So V by C ratio should be what? Less than 1. Clear? How much it can be? Okay. If you are making it 0.8, then you have lot of room available. Capacity is much higher than the demand or the volume. Okay. If you make it 0.95, they are almost equal. Got it? Clear? Okay. So if I want to use this as my capacity, first of all, I have to convert it to flow rate, meaning I will divide by the peak hour factor. Okay, and I want the capacity to be higher than the actual volume, then I will divide by my factor of safety as well. Okay, so I need to change this by dividing it with two factors, peak hour factor and volume capacity ratio. Clear? Clear? Okay. Now what in this equation, what I am designing, what is the parameter of the signal? Huh?
Phase. Peak of the phase.
Because per phase? No, no. What I am designing for the signal? Cycle length, yes. Okay. So I don't want the equation for VC, I want the equation for C. Okay. So we rearrange the equation. So first of all, we put C on one side, everything else on the other side. We will get this. And this equation VC is just as it is. Okay. So we need to divide VC by what? Peak hour factor and volume capacity. Got it?
Yes.
Clear? Any questions? Okay. Let us look at a couple of examples. Okay. We have a three-phase signal, loss time 4 seconds per phase. Saturation headway is given, peak hour factor is given, VC is given. They want the desirable cycle length, which is this one, using V by C in the range of 0.8 to 1. Okay. So what is N here? Tell me. 3. Okay, number of phases. What is TL? Okay. So N is 3, TL is 4 seconds per phase. Okay. VC is given, peak hour factor is given. Okay, what is H? 2.2, the saturation head. Okay. Now V by C ratio, they said change V by C ratio from 0.8 to 1. Okay. So what we will do is V by C. I'll try 0.8, then 0.85, 0.9, 0.95 and 1. Okay, I need the desirable cycle length for all of them. Okay.
Do we have to do it for all of them,
Yes.
or maybe go with your
Or
idea?
maybe you do it for all of them.
I got minus, so
Yes. Tell me. I love minus. Yes.
minus 660. Number 27.
The next one is the minus 648.
648. Okay. Which one? This one? Uh-huh. See, he was rounding off all the numbers. Huh? You guys are in competition. Huh? Why did he round off? I should round off all the numbers. Huh? 127 was not 127, right? 126 was something, right?
64.
guys read it, right? Okay. Okay, so you can see now, yes, for the sake of design, obviously, we will take one value. Okay, but they gave this question because there are some points to be explained here, okay, which will help you later on in the design as well. First thing you see is a negative value. Okay, this is our dream, our wish. That we can go back in time. What? No, some of us had good childhood. That's why. Okay. Huh? You will not be seeing me if you go back in time. Bonus. Okay. Sorry. Dimension number 4. Okay. So this is our wish. We don't have this. Okay. So negative. Okay, we ignore it. Okay, so this value cannot be taken. Why did negative become positive? Because we did what? The other values are positive, right?
Yes.
Why did they become positive? Because we did what?
V over C increase.
We changed the V by C. Okay, so if you get something like this, you can change the V by C ratio to get a more practical or possible answer. Okay. Then you look at the next value, 290 seconds, right? 290 seconds, so how many minutes? Almost? Huh? You should go back.
4 minutes, 57.
The person who told you there are 100 seconds and 100, it was wrong.
4 minutes, 50 seconds.
Okay? Almost 5 minutes, right? Okay? That's why I was looking at it. Yeah, without your calculator. How can you calculate? Your mind is not good. Okay. Almost 5 minutes, okay, which is too long in most of the cases. Okay. Normal cases, too long. Other one, 2 minutes, almost 2 minutes. Okay. So that's fine. The next one also, okay, practical. Okay, the other values are within 1 or 2 minutes. These are practical values. So you can take one of these. Now you see when I increase the V by C ratio, cycle length is decreasing. Okay. Now V by C is a ratio, right? V by C is a ratio. So increasing V by C means I am decreasing what? Capacity. You are decreasing capacity. You are going for less capacity, then you need less time as well.
Is that range?
You are designing for
There is a range of.
there's a range. There's a range.
Yeah, if it's
This
more
is the
than-
range.
No.
What?
Think about accepted values. It's
For?
than more, 1000
Accepted value for what?
for the seconds. So in device
Yeah.
it will be.
Yeah, in some books they have written 3 minutes, some books they have written 5 minutes. Okay? Which is like child's play for us. Huh? 5 minutes. Okay? Clear? Okay? It is given in the books. Okay? But 5 minutes is, I have seen 5 minutes to be the max. Okay? We have another example in which now you can see an intersection. The initial data of the intersection is given, the cycle length, the host time, number of phases. Now you see 2 phases. Okay. So earlier I said 2 phases will be very difficult to give. You can see the reason why they can give 2 phases. Huh? You look at the movements. How many movements are shown? Huh? They have not changed since last 8 years. Okay. So how many? What is this? Huh? 2, right? Are you looking at the same picture or not? This and this. Okay. This and this. 1, 2. Okay, everybody. So 2 phases, 2 movements. This is how they made it possible. Okay, so only one movement is allowed. Okay, only one movement is happening from each road. You cannot even see a left turn here. Okay, okay. So many of the movements are blocked. That's why two phases can work here, because you are only dealing with two movements. Okay, okay. So you can reduce the number of phases, but that also means the number of movements should also be less. Otherwise, it will become very difficult. Okay, or even unsafe as well. Okay. Coming back to the, so now peak hour factor is given. V by C ratio is fixed now. We will use this one. Okay, and saturation headway is given. Now what they are saying is, using this data, first of all, find out how many lanes we should give on the intersection. Okay, use this data to find out number of lanes we should have. Okay, and once you have fixed the number of lanes, then recalculate the cycle length. Okay, so use this one as initial value, first trial. Okay, and calculate number of lanes. Once you fix number of lanes, then recalculate. The next trial is recalculate the cycle length. Clear? Okay. Okay. First of all, I will calculate how much volume I can have with this data. Okay, I will calculate the allowable volume in this condition. Okay, to calculate the allowable volume, I will use this equation. Okay, so you have everything. Tell me the VC here. How much VC we have? One, 3, 5, 6 vehicles per hour. Okay, this is how much this can handle. Okay, any problem? No. This is how much this signal can handle that right now. Okay, how much do we actually have?
2,100.
It is still 3,000, right? What? No. 3,000, yes. Okay, 1,800 from here and 1,200 from the other side. Total, how much do I have? 3,000. Okay. How much can I have? 1,356. Okay. Clear? Okay. So I'm the volume I can handle is less, the volume I have is more. Okay. Now when we said we have 1,800 in this direction, okay, what do we mean? What are you discussing? Tell me.
Is it NTL or NL?
Sorry?
Is it NTL or
NTL or what?
NL?
NTL.
Both of you get your glasses checked. It is written NTL. Why would it be something else?
I can't say very well.
This is what I am saying. Yes. Change your glasses. Give him a black one. Okay. 1,800. Okay. So when we are saying 1,800 are passing from here, they are passing one after the other, right? 1, 2, 3, and then the whole 1,800 will pass. Okay. One after the other. So we are assuming how many lanes? One lane, right? One after the other. Okay. What if I make them go parallel? To make them go parallel, I should increase the number of lanes, right? Okay. So let's say I make 2 lanes here. Okay. So what will happen then? They will be divided. Okay. So I'm no longer worried about 1,800. Okay. Because they are now passing in pairs. Okay. So how many from one lane? 900 from each lane. So I don't have to worry about 1,800 now. I have to worry about how many? 900. Okay. Because those 900 will, the other 900 will pass simultaneously. Okay. So let's say I keep 900 in the east-west direction and keep the same for the north-south direction. So how much will I have? East west, now I'm worried about, or I'm dealing with 900, right? North south, I'm dealing with 1200. Total 2100. Okay, so if I give 2 lanes in the east west direction, then my demand reduces to 2100. Okay, am I looking for 2100? No, I'm still looking for even lower. Okay, now which direction has more flow now? 1200, right? Okay, so I will now divide this into 2 lanes. Okay, so it will become what? So now the total is 1500. Okay, did I meet the requirement? No. Okay, I'm still looking for 1300. Okay, so now I will increase 1 lane where? In the east west direction. Okay, so this will become how much? 600. The total was 1800, now it has 3 lanes, so it will become 600. 600 and 600 is 1200. I was looking for how much? 1356. So it's done. Okay, so 3 lanes in east west direction, 2 lanes in north south direction. Okay, one part of the question is done. What was the second part? Find out cycle length. Okay, now I know how much volume I actually have. My VC is now 1200. Okay, so now I will find out the cycle length using this. Okay, clear? Any problem? I know you have a problem with looking at board, but any problem other than that? Okay, so the final design is that you give 3 lanes east west, 2 lanes north south, and the cycle length is this much. Clear? Okay, any questions? Okay, now let's say we have a restriction from the government. The government says that we don't have enough space to provide 3 lanes in any direction. Okay, so the maximum you give is 2 lanes. Okay, can I give less than 2 lanes? No, I already tried it and it was not working, right? Okay, so I will go for the maximum, which is 2 lanes and 2 lanes. Okay, if I go for 2 lanes and 2 lanes, then how much is my flow? It was 900 and 600, right? Okay, then how much cycle length do I need then? Minus 66. Okay, so minus means what?
Not acceptable.
Not acceptable. Okay, so what can I do to change this minus into something else or positive? Change the V by C ratio like we did last time. Not the BC, V by C ratio. Clear? Okay, so these 2 examples show you how you can play with the geometry of the intersection or your design parameters to come up with a practical value, acceptable value. Okay, fair? Okay, in the previous examples, yeah.
We didn't solve the issue.
Which issue?
Like, if it's fixed 2 lanes and we have a limit
can change the feedback system. They did not ask.
So we make it 0.8 of it as well. That we
No,
need
if you go back, it will not solve. You have to go up. Huh?
0.95.
It will 95 or 1 or even between them. It's not doesn't have to be like a multiple of 0.05 and 0.96, 0.96, whatever gives you the right answer.
It's factor,
Huh?
correction factor if it's negative. It's correction factor if it's negative.
No, no, you have to change something in the design. Okay? And you can see the negative happened because of the number of lanes. The negative happened because of the number of lanes. Okay, so there are multiple things you have to look at for getting to an acceptable value. Okay, this was just an idea. Okay, in the previous question, the one which we just finished, when we were increasing the number of lanes, we were dividing the flow how? And we said we have 2 lanes now. Okay, so the total was divided by 2. Okay, so we are assuming what? Flow will be divided equally. Okay, but we know this is not how it happens, right? The flow doesn't divide equally. Nobody is counting number of cars. Let me go there. Now there are 51 here. Let me go there. Okay, it doesn't work like this. Okay, and what if you have lanes which are in different directions? Okay, so we are dealing with all lanes which are going in the same direction, but you may have a lane which is for straight and left both. Okay, then for sure it will not be the same. You may have one lane which is only for the left, and then you have 2 lanes which are for straight. Okay, so okay, you may say, okay, for the straight lanes the flow may divide almost equally, even if it is not exactly equal. If it is near to 50%, we can assume, okay, fine. But what about the left turning? It will not be the same as the straight. Clear? So if you have 3 or 4 lanes and then they have different flows, you will take one of them, right? Okay, so which one will you pick for your design? The one which has maximum flow, right? Okay, now let's say the flow is same. You have 2 lanes, one for straight, one for left turning. The flow in both of them is same. Okay, which one will you pick for your design?
Straight.
Straight,
Left
because you are on the left hand side.
because they need to slow down.
They need to slow down. They take more time. You are designing what? Time, right? You are designing cycle length. Cycle length is what? Time. So we have to consider the lane which needs more time. Which needs more time. Okay. So obviously left turning has more radius to cover, more distance to cover, and they will be slower as well. Okay. What else can make the flow slower? What else can make the flow slower?
Traffic outside.
Okay, if the traffic is the same, what else can make it slower with the same number? Huh? Accidents, okay, anything else which happens regularly?
Left intersection allows for both left turn and U-turn.
Okay, if they have more than one movement from the same lane, it will be much slower than having one movement only from the lane. Anything else?
They need to wait.
Huh?
Using what?
Using one, obviously.
They need for the
The radius
Anything
of
else?
the
Radius, okay. Maintenance, okay. All these things are correct. One more point which I was looking for was the heavy vehicles. Okay, you may have, and you know, heavy vehicles are, even if they are in the same direction, the lanes are going in the same direction. Okay, they are supposed to be in one particular lane. Okay, so that lane, even with the lower number, because of the heavy vehicles, may need more time. Okay, so the point is, you should design for the lane which needs more time, because what can happen, you design for a lane which actually needs less time and the other lane is not satisfied. You have a long queue in that lane because you did not consider it, the slower lane. Okay, so the lane which you take for your design is called as a critical lane. Okay, so if a direction has multiple lanes, you will see which lane needs more time and you will take the flow from that lane and your design will be according to that lane. and that lane is called as a critical lane. Okay. So every phase will have a critical lane, and the timing will be calculated according to the flow in that lane. Okay. Some more points about critical lane. The first point I already mentioned, that every phase has a critical lane, and it cannot be more than one. Whenever you have effective green, so what is effective green? You have the total time minus the lost time. Okay. So in the total effective green time, at least one critical lane should be open. Okay. Because every phase is for a critical lane, right? When one phase closes, the other one should open. So one critical lane closes, the other one should open. Clear? Okay. And then there are lost times as well, where this may not happen. Okay. But in the remaining time, the critical lane, at least one critical lane should always be open. Okay. Then we have overlapping phases. Overlapping phases are those in which you allow different directions to go at the same time. Okay. For example, two straight movements in different directions, they can go together. Okay. We have it on the what is this road? The Zalak highway. Okay. So they allow two straight movements to go at the same time. Okay. So this is overlapping, because this is another direction. These are two different directions, but they are happening at the same time. So this has one phase, one critical lane, one phase, and the other direction has its own phase and other has its own critical lane. Okay, but they are going simultaneously, so we call them overlapping phases. Okay. Any other overlapping option? One is two straights. Two lefts are also. Okay, these are also overlapping phases. Okay, that is also allowed sometimes to go at the same time. Okay, now let's say I have okay, so let's say I have this movement. And I have this movement. Okay. This one is, let's say, 400. And this one is 500. Okay. And then I have two left turnings as well. And their volume is, let's say, 600 here, and 500 here. Okay, so I have options. I can go for this overlapping or this overlapping.
I didn't understand.
Okay. Sorry,
I didn't understand
which one? Two straights, two lefts, two left turns.
They go against each other.
Oh my God. Yes, this is what I wanted. I want to kill everyone. It's just a sketch. Don't be serious. Okay. So, which option of overlapping would I go for? Okay. Why this?
Because slower.
Slower, not because slower. When you are dealing with overlapping phases, you sum the movements which you are allowing together. You sum the movements of the critical lanes which will go together. So I have a critical lane here, critical lane here. This one has 500, this one is 400. If they go together, total volume which will go together is 4 plus 5, 900, right? Okay. If I allow this one and this one together, this critical lane has 500, this critical lane has 600. Total is 1100. So which overlapping is more beneficial? Which is allowing more volume to go together. Okay. So this is how you can decide for the overlapping. Okay. So for overlapping, you may have different options. Which option is more beneficial? The option which has greater sum of critical lane volumes.
We don't take into consideration the direction.
That is already done, right? When you selected the critical lane, that is already done. So for this phase, this is the critical lane. Okay, this is the volume in the critical lane. So for this direction, this one is the most important one. The timing, the direction already considered. Okay, and so on. Okay, clear? Okay. When we were dealing with highways, freeways, multi-lane highways, okay, so we are talking about free flow speed, density, flow rate, and so many things. Okay. For intersections, we cannot talk about these things because at intersection we force the flow to stop. So when you are forcing the flow to stop, the flow becomes what? 0. The speed becomes 0. The density becomes highest. Okay, but it's not highest because of traffic, because you forced it. Okay, so we cannot use the same parameters for measuring the performance of the intersection, because all these parameters are forced by us. Okay, so then we come up with other parameters which can change on the intersection, such as delay, such as queue, such as stop. So all these things happen at the intersection randomly. Okay, so these are taken as the measures of effectiveness or measures of performance, the values which indicate if the intersection is good or bad. Okay, so for example, delay. More delay is good, right? Longer queue length. Okay, so longer queue is weak performance. Okay, number of vehicles or percentage of vehicles which stop on the intersection or on the signal. Okay, so these measures are used for finding out the effectiveness or performance of the intersection. Clear? Okay, so we will talk more about this in the next lecture.